Okay, so thanks, Peter, for introduction, and thanks the organizer for the opportunity to give the talk here, and thanks all the speakers before me to whom I was able to listen for nice talk. And okay, so I was overly optimistic when giving the abstract of the talk. Okay, so anyway, it's something on a joint work with, still ongoing with Jan Pullman. And Martin Zika. With the generous input of Pavel Severa. Yeah, okay, so I just names, okay, well, of course, important, of my former students. Okay, so as I said, there will be some notes on what a category of BV theories and eventually, well, which is from my point of view the same as quantum L-infinity algebras could be. So essentially, there will be some motivation with some attempt of a definition and maybe some examples. And, well, okay, some list of wishful items. Okay, so for those who are not familiar with, let's say, quantum L-infinity algebras or BV formalism, so let me start with a brief recap. Okay, so on one hand side we have Q L-infinity algebras. You can think of a quantum versions of cyclic L-infinity algebras, sometimes also known under the name of loop homotopy algebras. And so what is the setting? We have a differential graded vector space V, which is equipped with an, okay, Q is my differential. It's like Q from BRST. Okay, and it's equipped with an odd symplectic vector form of degree -1. And of course, Q and omega are compatible. So the Lie derivative with respect of the homological vector field, to think of Q as homological vector field, is 0. And then we have operations, n-ary operations. For each G, you may think of G as genus. That's the natural interpretation in BV, and also from point of view of operats, because this comes as operats over the Feynman transform of modular commutative operat. Which have an input and one output. And there is a bunch of relations for those kind of natural ones for those operations to fill in. I will not write them down, because if we switch to the equivalent description using Batalin-Velkovitsky formalism, the meaning and the relations will become obvious. So anyway, maybe I should say. Sorry? Sorry? Q is linear. So far, Q is linear. So Q and these operations. You can. It's okay. Sorry, I should have said this. Of course. Thank you. So that's M2, M1. M10. Yeah, it's M10. It's the linear part of the, will correspond to the free action here. Oh, no, part of, there is, part of the definition is also the compatibility of the higher ones. I didn't say there is relations which are fulfilled by those. Yeah, I will do it here. It just, I don't want to bother you with this explicit. Sorry? No, that's correct still. There is another one. Yeah, okay, yes, another one. There is no. That's my. No, okay. Yeah, so I mean the equivalence is including all these. I don't write down, so there are, some, yeah. There are dots. Okay, there are dots. There are dots. No, thank you for asking. Oh, it's good to, clarify the things at the very beginning, of course. Okay. So, like to be safe, of course, for me this will be degree-wise. It's a graded one, so degree-wise it will be finite dimensional. So essentially, I'm doing 0 plus 0 quantum field theory, right? So I don't run in trouble with exactly. Yeah, it's finite dimensional. I needed, yeah. Well, that's one possible, yeah. Some people call it finite. Some people call, yeah. So I don't have to care about, like later my Batalin-Wilkowiski operator not being defined, and yeah, some people call it finite, whatever. Yeah. So anyways, one of the reasons, of course, it's, besides that everything will be well defined, also I mean, going from here to here, I have to dualize, and then I can dualize component-wise. Yeah. They are graded. They are all the dots. They are graded. Yeah, okay. So maybe I should write the symmetric and symmetric power. Would be more appropriate. But I can have also a version for other homotopy algebras. I can start with any modular operat, take its Feynman transform and do an algebra. And I would get, let's say, quantum A infinity or quantum combination of A and L or quantum C or whatsoever. But let's leave this for the future. Okay, so here what we have here is, we can combine these operations into Batalin-Wilkowiski action. So how we do it? So we have S is a sum over Ng and G, and so S and G is like H over G. It's the meaning of the genus name is clear. It counts the loop corrections. And now what we can do, okay, I first write the formula and then I explain the notation. So we have our operation. Okay. Okay. Then I need -1. Okay. N and G. So, like you see, it's like the endpoint vertex, and I don't know, genus G. So, what's the Schoenstatt from the notation? So, this is what, for example, physics people would call string field. So, it's a canonical element in the V dual. So, take a basis, a homogeneous basis of a V, take a homogeneous basis of V dual, the dual one, and that's your string field. Oh, V is a graded space. It's a graded vector space. No. Phi is just really so far just the coordinate functional. Just the, oh, but okay, these are dual ones. They combine to 0. This has the opposite degree as this one. Oh yeah, but well, I switch when I find it useful. It's just now vector space and the dual vector space and the dual basis. The phi is the canonical element. Well, yes. Yes. Well, oh, there are no commutation relations yet. Well, once I introduce the Poisson bracket, then yes, there is a Poisson bracket on phis. Well, I should explain, but this is polynomial of degree n. It's a product of phis. Well, they are graded antisymmetric. It's symmetric functions on V, that's all. Exactly. Exactly, that's all. There is no it's nothing deep, right? Yes. Exactly. Yeah. Phi is a map. I'm writing you, yeah, I can, well, it's like you write the polynomial in like a product of of coordinate functionals which are eventually evaluated at a point to get the number. Yes, that's it. Nothing more. It's the identity. Therefore, I call it canonical element. These are coordinate functionals on V. On V. On the graded space. Yes, okay. Yes, okay. So you think of the graded, free graded algebra generated by phi modulo the relation by graded symmetry. The idea, yeah. Exactly. Okay, fine. Okay, good. Think of it whichever way you like. So explicitly, using the string field, what you do, you take the first factor, you plug it in your operations. So you get something in V, you have symplectic form, you can contract it with another one, and just multiply with the phi's. So that's what the formula says. It's just compact. So it's kind of essentially generating functions for these operations. And so the point is that for this M and G fulfill the axioms of the quantum L infinity algebra, this is equivalent to say that this is a solution of the quantum master equation. So sometimes I will omit H, well, maybe for the time being, I keep it. Sorry? Yeah, good question. But I have omega. So it's given by the inverse of omega. Omega. So this is the inverse of omega, and this defines you the second order differential operator. Sorry? Yeah. So this constant. So far, yeah. It's just a symplectic form on a vector space. So that's the delta. Well, you can do better, of course, if you wish. You can go to manifold, and eventually one day I would like, but. Sorry? I will come to that, of course. Of course. Yeah. Well, that's motivation. Yes. Yeah. Yeah. Yes. No. No, these are all these G's. These are all the G's. The classical would be just put only keep G0. Yes? Yeah, that would be the Q. No. Okay, so I'm going to write this. So there are several equivalent ways. So one is, of course, the quantum. This is the quantum master equation. Or you can have, well, not the homological vector field, but homological second order differential operator. So you can combine delta with the Hamiltonian vector field. Probably put it here. And this now squares to 0. That's what you know from textbooks on quantum field theory. So these are equivalent ways too. Exactly. Which corresponds here that you have here. You can put consistently all M and G for G greater than 1, 0. And in particular, we have the S3 here, which is S0, but now 2, which comes from Q. Q is linear, so it's linear, you get something quadratic. Okay, so it's good that we have these 2 point of views, and we can kind of switch from one to another whenever you like. And if you remember how the axioms for an L infinity algebra look like, it's not all. You have extra terms. It's ugly. It's ugly. Therefore, you plug it in, you expand it, and compare coefficients for each N and G, and you get your relation. Yeah. And the signs and everything. Here you have everything packed nicely, you know. Okay. So having two such BV theories on two quantum L infinities algebras, so what we would like to have, like, the morphisms to include, right? So that's the first question. Of course, again, motivated by, let's say, quantum field theory, field redefinitions should be morphisms, right? So what are, well, field redefinitions? Okay, we have now two PV theories. And so okay, start with this case, V. And so then, of course, first of all, since we have this symplectic structure everywhere, we would like this to preserve. So a honest diffeomorphism, a symplectomorphism. So one thing we would like to have as a morphism would be symplectomorphisms, which are by definition diffeomorphisms, such that if so, B. But we have still two different symplectic structures. So if we pull back omega 1, we get omega 0. And, well, what happens with the actions? We would like also relate actions. So had it been a classical case, we would get S0 as a pullback of S1. But now there is more because, well, this is this Bartalin-Minkowski thing floating around, which tells us that we should, well, get the familiar 1/2 of logarithms of the Berezinian of phi. So that's how the actions should be related. Now, okay, I should compute the Jacobian and take the Berezinian determinant. Sorry? Okay, so I should be precise. Okay, so there are different choices, which I don't bother with. Yeah. Of course, this is from the integrations of supermanifold, right? You have different, yeah. It's not unique, I know. It's not unique, but keep it kind of. In different cases, you would have to choose. Yeah. oh gosh, it's finite dimensional. So in general, like you have how many components? You have this 0 and 0, 1, and yeah, that's a fine. Yeah, then probably not that many. Yeah. But of course, if I go to manifolds, then I would have to care about this. Okay, so maybe there is a nicer way to write it. So you can now consider half densities. So where this things comes from is that you have to pull back half densities. So this relation, it is actually the same as saying that S0 over H. Now I have to take the half density, and then this is the pullback of the half density. And well, now you can work out properly which Bayesian you have to take. Or, of course, another way to say it is that the phi intertwines between the respective Batalin-Minkowski operators. So have I written it down? So maybe so it's H delta 0 plus S0 0 here. I can pull back a function, apply it to it, or I can do other way around. And I should get the same. So again, this Bayesian comes now because we have these deltas here. So it's not just something which intertwines the vector field to intertwine the differential, the second order differential operator. Okay. So where these things come from? Of course, if you do Batalin-Minkowski quantization, these are natural things we will get. So maybe I can make a bit comment on that. So we can do, in the language of Batalin-Minkowski algebras, we can do BV perturbation theory. Or on the quantum L-infinity algebra language, we can do like homological perturbation lemma. So constructing minimal model, or like formulating a decomposition theorem. Okay, so what we do here, we compute the effective action, which is a function. Okay, I should say, of course, in this setting, we always have a Hodge decomposition of our vector space V. So we have Hodge decomposition. Yeah, so we can decompose our V into the cohomology of Q, into the image of Q and the complement, such that these are compatible with the symplectic structure. Somehow. Okay, so omega descends to H. So if you omega is written as omega on H plus an omega, call this, I don't know, H prime, some complement, or V prime maybe is better. V prime. Well, now, yeah, this is, well, where these are Lagrangian subspaces. And these are Lagrangian. So it's just some linear algebra. Okay, so maybe also yeah, it is. It is because omega is compatible with Q. It follows immediately. Yeah, because LQ omega means that this is the same plus minus as and from that it follows. You insert two Qs, Q of something, Q of something else. Now you use this, you get Q square, and this is 0. Q squares to 0. Sorry? It's Hermitian with respect to. Well, that's the contents of LQ of omega is 0. It's this one. It's this one. Omega is closed, obviously. Yeah, well, it is. Okay. It's Q is a linear operator, yeah. It's okay. It's a vector field, yeah. Yeah, that's all. It preserves the symplectic structure, and that's the condition. It's okay if you don't like this way to write it. Oh, this is the. Okay, well, so I guess I will not get too far today. Good that you ask anyway. Okay, so this is some function on the cohomology. Okay, maybe better to write formal power series in H. And so what you would do in like field theory is you would compute the integral well, where C is this complement here. You integrate, so you put everything in image to 0. This is your gauge choice. So everything which is an image of Q, you put 0, and you integrate over C, and you get a function on the H. Which is, well, actually a nice exercise to prove that if you do homological perturbation lemma, so here we have the projection P, which goes from V to H, and we have the inclusion which goes from H to V. Okay, and here it is on vector spaces, and it uses the thing, algebra morphisms on the functions. So I use the same letter, but I hope it's not too confusing. Minus. So this is what perturbation lemma would tell you. You do this geometric expansion, take the interaction part, which is everything in the action except the free action. Or, which is the same as we know, you take the exponential of the propagator. Well, since you have Q, Q has a quasi-inverse here, so you can take the inverse, which defines you the propagator. So you take on the propagator, which you can think as a second-order differential operator on coordinates on C with constant coefficients, which does the contractions for you. And okay, so there are different ways how to write it. So maybe you know this under the name of Losseff's trick, right? Or fiber integration, fiber-wise integration. read Nev's book or papers, for example. Well, here it is a honest integral. No, that's the definition. That's the definition, the first one. Yeah, and these are equalities. Yeah. Oh, yeah, that's the if you wish, this is the stationary phase around the vacuum. Yes. Yes. Yeah. Yeah, absolutely. Yeah, this makes perfect sense. Even on manifolds do this, as you say. Well, it's an old article by Schwarz from 78 or something like that. Sorry? Oh, yeah, he starts with classical equation, classical, yes. That's usually in quantum field theory, unless you do like string field theory or something where you need all these extra higher powers of H already from the beginning. If you think of ordinary quantum field theory, yeah, you have no G there. But you get it, of course you get it here when you evaluate because, yeah, you do also Feynman diagrams for loops. Okay. So the point is that since your omega restricts to H, so you have also Batalin-Volkovitsky delta on H, and it's easy to see that what you produced is a solution of the BV equation on cohomology. So you can think about as like S matrix in quantum field theory. Okay, so can I continue here? Okay, so maybe, so this is just, so what you produced, you started with an, let's say, L infinity, quantum L infinity algebra described by S, and you got another one on cohomology, which is quasi-isomorphic, so you got a minimal model. Sorry? For example, from the homological perturbation lemma, it is. So if you start with quasi-isomorphisms, you get a sorry? Oh, well, okay. No, yeah. But that, okay, so this is why I'm, my starting point is what is the category, because to talk about, minimal models and stuff, I would need to have a good model structure on my category. I don't have it. I call this minimal model because it transfers the original structure to the cohomology and is quasi-isomorphism. So, yeah, people object to calling this. Like Martin Markov is always furious hearing that. No, what I am claiming, you blindly apply homological perturbation lemma. This gives you that. And there is a little, sorry. Okay, so this is, okay, I should have told you. Okay, this is contracting homotopy. I have my starting vector space VQ. I have my projection and inclusion of the cohomology. These are quasi-isomorphisms. And now I can perturb Q with delta H. That's the delta, that's the Batalin-Wilkowski. And here I have the contracting homotopy. So HQ plus QH is IP minus 1. The point is, I have this always. If I have here even one quasi-isomorphism is enough, I have always contracting homotopy. Delta? Well, yeah, that's delta restricted because omega restricts. I use just the inverse. I use just inverse of this omega. So it's just piece of the second order differential operator which takes, with respect to variables in H. Oh, it induces, okay, exactly, on functions, exactly. You use the tensor trick, you can symmetrize, yeah, and it allows you to define, exactly. A good point, yeah. I always forgetting these things, which I don't know. Yes. Exactly. So you blindly apply, so you leave this to the symmetric algebras, you blindly apply perturbation lemma, you get this, and you get this. From homological perturbation lemma. No, I'm not saying, I'm constructing, the point is that I get here a perturbed differential, which is H bar delta H. And this is done in such a way that it goes between, if you wish, Maurer-Cartan elements of this one to a Maurer-Cartan element of this one. Okay. Using perturbation lemma, this is my new projection coming from the perturbation lemma. Perturbation lemma produces you with the new contracting homotopy, with the new perturbation, with the new projection, new inclusion, new H bar, and that's expression for the new projection. And I am claiming it's done in that way that if I apply it to a solution of master equation, this one, well, this is, because I subtracted here the free part, I have to put the Q here. Well, that's how I do perturbation lemma and how you do it, how you do the contractions. So the point is that I claim I get a new projection. If I apply this projection, the new projection coming from perturbation lemma to E of the interaction part of my action, I get something which automatically fulfills the quantum master equation on the cohomology. That's the statement of the perturbation lemma. The things either here and here in this equality, they need some little work to prove that they are indeed the same. You can do either combinatorics, expanding this, looking at the Feynman diagrams here and comparing them with the Feynman diagrams here. Sorry? Well, that's finite dimensional. So, okay, I assume, well, I'm doing now perturbation theory in the sense of perturbation theory around 0. It's the Berezinian integral, absolutely. But it's finite dimensional Berezinian, so it's, and of course I assume that, well, on C, well, obviously, my quadratic part is non-degenerate, right? On C, where I integrate over, and has proper sign, so that, yes. Right. Because I started with finite, yeah, by assumption. Every degree is finite dimensional. So it's well, of course, an infinite bunch of finite dimensional integrals. Those are functions. Functions. Oh, sorry. So I just wanted to say that I get element here. This one, automatically. So therefore, you get another quantum L infinity algebra on the cohomology, which is quasi-isomorphic by construction. Well, that's in the quantum. You can do also, well, it's a bit... Well, this means that I put everything which is on an image of Q0. I integrate over this Lagrangian subspace here. That's the gauge fixing. It doesn't depend on imaging. Yeah, but that's the usual notation, right? You integrate over Lagrangian subspace. Yeah. Yeah, in this W part, these are Lagrangian subspaces, both of them, yeah. Yeah. You put everything. So if you wish, you have some coordinates. You have coordinates. Well, it's included, I mean, in this notation that I integrate over. So, okay, this means that, okay, so delta half density, delta half density is supported on C. Okay, that's, and then I integrate over, yeah. Oops, I'm sorry. Okay, but actually from this homological perturbation lemma, you also get the decomposition theorem, which says you that you have a diffeomorphism, which you have a diffeomorphism from which way it should go now. Gosh, yeah, it's still from V to V, which is symplectomorphism, and well, interpolates between original action and the free piece plus the image of W. So this, in the proper sense, as I wrote, with this 1/2 of logarithm of Berezina. So this tells you that you have a decomposition of your original quantum L infinity algebra into the minimal piece and into the contractible piece. So these are examples, and I would like to have this, which come naturally from. So this one, so the minimal model is actually, it's not a symplectomorphism, but it is a Poisson map, because it's a combination of this diffeomorphism and the projection to the H. So another thing which I would like to include is things like that, where I don't have symplectomorphism, but I have a Poisson map, which intertwines between, let's say, I guess what would be maybe the easiest way is to, which intertwines. Yeah, that would make sense, right? Even if phi is not a diffel, just a Poisson map. Okay, so maybe this this leads us, this was enough of motivation, and this will lead us to to an attempt for a definition. Okay. So, but since there were great men in the not distant past, like Alan Weinstein and Pavel Severa, who gave us already the hint what we should do. Because you see, the point is that we after all, what we have to do first is to take care of these symplectic structures, right? Because, you know, symplectomorphisms are too restrictive. You get only diffeomorphisms by definitions. And also the Poisson maps, actually, if you think of Poisson maps, they go always only in one direction relative to dimension, right? You can, yeah. So, and you would like to have something more symmetric, right? So the hint is look at this symplectic category of Alan Weinstein in this setting. And so, who? Zakrzewski. Okay, good. Yeah. So should get his credit. Kashek, right? No? What was first name? I knew him very well. Okay. Kashek, I guess. Yeah. But yeah, he died quite young. Okay. So let's consider two symplectic, odd symplectic manifold, M and N. Oh, maybe. Okay. And so this would be, okay, maybe since I would like to talk about the category, quantum odd symplectic category due to Severa, right? So objects would be odd symplectic manifold, and morphisms in his category are so generalized, or if you wish, distributional half densities. Sorry? Just words. You know what is a half density, right? You can define it. They are not maps. That's the point about the symplectic category. These are these correspondences or Lagrangian canonical relations. Lagrangian correspondences, whatever. Yeah, that's, yeah. So maybe I'm rushing too much and not being very consistent, but yeah. Morphism, okay. That's the definition. It would be distributional half density supported on a Lagrangian subspace. So that's okay. It's a density on, okay, M1, M2, if you wish. So I think of this about, but here it's not of importance, but this is a symplectic manifold where this has the minus symplectic form. And now I can look for half densities on that which are supported on a Lagrangian submanifold here. Well, which is Lagrangian relative to the symplectic. Well, essentially delta functions. Delta functions. Well, essentially, for now, I will use only delta functions. It's, you know, like over there. Oh, okay. Yeah. Everything should be smooth. Yeah, of course. Yeah, I run into these same problems, of course. Exactly. Okay, and so how the composition works? So, okay, so this, if I use this notation, right? Okay, so I just say it in words because I'm running out of time. So if you have two such morphisms, so you think here of the third one, M3 omega 3. So you can take these two half densities, one this one and another one where you have now M2 opposite M3. You just, okay. If you, should make sense of multiplication, but if you multiply them, what do you get? You get a half density on M1 times M3 and a density on M2. And this is what you can integrate. So you integrate this product of these densities over M2, half densities, and you get a half density on M1, M3. So that would be the composition, how you compose. The multiplication is the convolution. Exactly. And of course, again, if the composition of my Lagrangian submanifolds is again a Lagrangian submanifold. Okay, so the point is that, as we know that on half densities, okay, so that's not, okay, that would be the definition. And moreover, a well-known fact is that on half densities, in general, densities, we have Bartalin-Wilkowiski delta acting. So if you have whatever half density on a symplectic, graded symplectic manifold, you apply delta, you get again a Bartalin-Wilkowiski. Well, essentially, if you think, as I wrote this kind of half densities, you can imagine it like this would be my half density. So delta is the ordinary delta defined to the function multiplying this half density, which in my case for a vector space, it was just the dv is. Okay, so it's defined in paper of Kuda-Vendrian, for example. So you may look it up. I don't have time to define it. The point is that you have a good Bartalin-Wilkowiski delta. Well, it's kind of still a motivation. It's a preliminary definition, which needs a lot of work to make it. That's an attempt. You may not like it, but this is a well-defined. It's canonical.